In this video, I'm going to talk about AVL trees. Let's say we have a binary tree. For any subtree, we have a value on the root that is x. And this node has left subtree and it has a right subtree. If every node in the left subtree is less than x, and every node in the right subtree is greater than x. So we assume all the numbers are distinct, and this is the root. If you have a binary search tree, then searching for an item, let's say I have an item y comes in. I compare y with the root. If y is less than the root, then I definitely go to the left subtree. And if y is greater than the root, I will definitely go to the right subtree. If y is equal to the root, that means that we have found it. So if this tree has a high h, then searching for a number or for the key in the tree will take big O of h steps. Hence, we want h to be as small as possible. If we have n nodes, then the best we can hope for is that h is in the order of log n. Then it is balanced. An AVL tree is a balanced binary search tree. So now we're going to see how we are going to balance a binary search tree by using the construction of AVL tree. For any node in the binary search tree, let's say this is any node, and then we're going to look at its left subtree, and we're going to look at its right subtree, and then let's say I have a height, let's call it h. L, that's the height of the left subtree, and let's call this HR, that's the height of left subtree for this node. We want HL minus HR, so either -1, 0, or 1. Right? So if this is true, then this binary search tree is an AVL tree. Okay, so this is also called a balancing mechanism, and sometimes we call it a balance factor. Let T be and node AVL tree with height h. We want to show that h is less than or equal to some constant times log n. We can just look at the smallest AVL tree with high h. And then we want to know how many nodes in that tree. So we let n h be the smallest number of nodes for an AVL tree to have height h. So then we know that and h is less than or equal to n because T is an NO AVL. So then now we have NH has to be in this form. So you got a root. And it has a left subtree or a right subtree. One of them must have high h minus 1. The other one must have high h minus 2. Okay. So in other words, the difference between the height of these two subtrees have to be either -1 or 1, cannot be 0. If it's a 0, then it is not the smallest AVL tree with height h. So NH is equal to 1 plus NH minus 1 plus NH minus 2. We write up NH minus 1 using this recurrence relation, then we get 1 plus nh minus 2 plus nh minus 3 plus nh minus 2. Okay, so as we can see here, we got two copies of nh minus 2, and this is 2, and this is non-negative, so it's greater than 2 times nh minus 2. Okay, so we can do one more iteration. So this is a 2 times nh minus 2 minus 2. This is going to be 2 times 2, and then this is h minus 2 times 2. For this is from the exponentiation, and this is not. So which means that if you do one more iteration, you can see this is 2 to the 2, and this is 2 times h minus 2 times 2 minus 2. So it is now it's going to be 2 to the 3 and h minus 3 copies of 2. So it's 3 times 2. So this 3 and that 3 is the same. So that means that after k iteration, you have 2 to the k and sub h minus 2 times k. When this is equal to 0, then we know n0 is 1. At 0 height, there's only one node, so that's 1. So that means that when k is equal to h over 2, then n0 is 1. So which means that eventually you're gonna get 2h over 2. Now remember that nh is less than or equal to n, and so what we get here is that h is, you take log at both sides, right? So this is n greater than or equal to this, and that means n is greater than or equal to 2 to the h over 2. So you take log at both sides. So then h over 2 is less than log n. So h is less than or equal to 2 times log n. Okay, so this proves that the AVL tree is balanced. Now let's look at how to build an AVL tree using binary search tree insertion. To begin with, we have one node which is balanced. And then we have a second node comes in. So this is the first number in the list, and that corresponds to the first node. And let's say we have a second node comes in, and the second node will either become a left child or a right child. This is also balanced. And the third node comes in, then it could have this scenario. Then this is off balance, or we could have this scenario, which is within balance, or we have this situation that's off balance. In this situation, you just need to rotate this, and then you can move this one up. For instance, we can say this value is small a, small b, small c. In this case, this means that C is less than B is less than A. Move B up. This is still a binary search tree. In this case, I have A is less than B and is less than C. We do a right rotation on A. So in other words, this B becomes the root, and this is within balance. Now let's say we have the following situation where previously we have an AVL like this, and then the new node comes in. That new node, it's either here or here. This is off balance because, as you can see here, the node, let's call this blue, and this is green, and let's call this A, B, C, and this will be my new node either here or here. In any case, we can see this three nodes, blue, green, and on this path, on this path, or on this path. Look at its child and its grandchild on the path where the node is inserted. They are in the same direction, either here or here. In this case, we just need to rotate the blue node down. That means move the green node up to the following. And this is X either here or here. And B now will become the left child of blue because B is less than blue. And this is C. So this is balanced. Now let's look at the other situation where X is inserted as a child of B. X is here or here. And if we look at the path from blue down to this X, either here or here, the blue is the first one that's off balanced. In this case, B is equal to 2 because the left subtree of the blue is taller. And you look at this three consecutive nodes on that path from the one that is from the one from X that's first off balance. They are not in the same direction. If you try to move as before, move the green node up, that means the blue node down. So what you end up with is the following. And as you can see here, this is still off balance. And this time it comes from the right child, from this part. Okay, so this is B now is -2, which means now we want to move the green node down by moving the blue node up. So that goes back to the original tree that we started with. So we are in the circular situation, which means that we cannot simply do this. Instead, what we should do is to first line up these three consecutive nodes into one direction by moving B up. So in other words, we do a left rotation by moving B up to get B. This is still C. And then the green node will go here. So green node is smaller than B, so it has to be the left child of B. Okay, so this is A. And then um, the X will come because X is greater than uh, green. Okay, so we can move our X here. And if X is on the right of B, then this X is here. We're gonna move B up. That means we do a rotation on the blue node. So we get B, blue, and green. And so this is C, this is A, this is X, or this X is less than the blue, greater than B if from this dotted line or in here. So that way we store the tree balance. Now we are going to look at the other situations where it means that the tree is off balance from the right-hand side, which is actually a symmetrical situations uh, to the ones we already seen. So this summarizes what I said earlier. In this situation, which means that the new node X is inserted so that now the blue node is the first one from the inserted node on the same path. Okay, and that's off balance. And look at the same path. It has its parents, grandparent, and the blue node. These all three nodes are lined up in one direction, then one rotation is enough. Likewise, if X is inserted as a right child of A, these three nodes are still in one direction, so are using the same rotation. The other situation then would be this X. It becomes a child, either left or right of B. So from that path, from the inserted node, you trace it back to the first one that's off balance. They are not in the same directions. In this case, you will need to do two rotations. The first rotation is to make the three nodes into one direction. So now you see that this becomes one direction. Then you need one more rotation to restore it back. Here is a concrete example. Here's a concrete example of inserting these nodes. And as you can see here, so the first one is AVL, the second one comes in is AVL, but the third node comes in, that's 3. In this case, is on the right side of the root that is off balance. You will just need to move this 3 up into the same direction, and then you can restore that tree. The next node is 10. It's still AVL, so this is AVL. So the next number is 5, and 5 goes in here. And then we check the first node that's off balance, which is this. And they all lined up, so then we can just use one rotation. The next number is 8. So 8 comes in this way using binary search, tree insertion. And in this case, this node is the first one that is off balance. And you look at the 3 consecutive nodes, they are not lined up in one direction. So you want to lined up first. So rotate 5 up and then do another rotation to restore the tree back. The next node is 7. So when 7 comes in, it's still within balance. And when 6 comes in and it is off balance, then the first node that's off balance is 2. So you look at the 3 consecutive nodes on the path where the node is inserted. they are in the same direction, and then you just need one rotation to restore the tree balance. Okay, so this is from the previous one, and now 9 is inserted, and we look for the first one that is off balance. So this is the first one, and we look at the three consecutive nodes on the path where the node is inserted. They are not in the same direction. You need to rotate so that to make them in the same direction, and then do another rotation. Then you can restore the balance. And also the property of BST. Then 4 comes in, that's within balance, and 11 comes in, that's off balance. And the first one that's off balance is this node. Then you look at its, so this is the path. You look at this three consecutive nodes, and then you see they are in one direction, so you only need one rotation, and you will restore the tree balance. And then when 2 comes in, it is still within balance. Now, let's look at Python implementation. First, we augment node structure. This is BST node structure. You got the value, you got a pointer. So this is left pointer, and this is right going to its two children. And then for AVL, we will add a height, and then this is left, and this is right. Okay, and then we can implement left rotation. Whenever we do a rotation, we need to recalculate the height. So that's here. Either we do a left and then we do a right rotation. And after that, we can do insertion. So insertion, we first follow the binary search tree insertion. After a node is inserted, we update its height, and then we compute its balance factor. And then we check the first one that is off balance, because this is a recursive call. So the first, so we check them. If it's a if B is equal to 2, which means that it's off balance from the left side. If B is negative 2, the off balance is from the right side. They are symmetrical. We just need to check whether the node that's off balance, we check it's is from the left. Then we look at its left child, and then we look at the child on the path of the node that's inserted. So this is off balance. We are in here, and then the key is inserted. So we look at this child, whether it's here, right? So we look at these three immediate nodes. The key could be here, or could be this. Okay, either way, then we just need one rotation. In this case, we do a right rotation. Okay, so either this or this or that. But if it's greater than the root value, so that means the key will be here, either this or here somewhere, right? So in that case, these three are not in the same direction. Then you will need to do a left rotation first, and then we do a right rotation. That's the end of this video. Thank you for watching.